I'm glad to introduce the first speaker, professor of St. Petersburg Peter the Great Polytechnic University, a corresponding member of Russian Academy of Sciences, and last but not least, my teacher, Professor Anton Krivtsov. Please, you have
Thank you very much, Alexei.
45 minutes, including the questions.
Okay, thank you. Dear colleagues, my lecture is devoted to non-steady heat transfer and possible variants of this transfer, as you see, ballistic or diffusive. So what is it? On the first slide, you can see an example of two types of wave transfer. Because when we speak about heat transfer and energy transfer, usually this heat and energy, at least in solids, is passed by waves. And waves on the surface of the water, Nikolai Nikolaevich, if you could, I would be very glad if you also could hear this. So you can see here an example of waves from the just stone which is dropped into the water, and it goes like without any obstacles. You see these rings. Another way, if you have a lot of rocks in the water, you will have something like this diffusive picture. So the difference between ballistic and diffusive processes, transfer processes, are due to appearing of obstacles which reflect the waves. If there are not obstacles, we have some like ballistic transfer, like if we speak about electric current, we can have ballistic transfer of electrons, and if we have electric current in solid, we have obstacles, and again we will have diffusive electric current. The same thing is with heat transfer. When we try to analyze this analytically, diffusive heat transfer is described by the Fourier heat equation, which gives you, in the case of the these initial conditions rectangular, you will have something like Gauss curve. And if you have ballistic heat transfer, and in the simplest case of Hooke chain, it can be described as this equation, then you will have absolutely different behavior, and you will have something like waves. And what is very important, that here the front is propagating with constant speed, and here the growing of this heating zone is proportional to the square root of time. So this is absolutely different processes. Now these problems, especially in discrete media, were analyzed by classics. For example, this is a very interesting paper by Ilya Prigozhin, the Nobel Prize winner. And this is also a classical paper by Joel Leibovitz and co-authors, which actually was one of the first papers on the ballistic heat transfers in simple chain systems. This is a recent book on the heat transfer in nanoscale, where many of these processes are analyzed. What is important, if we try to analyze what is happening in solids when the heat and energy is transported, to describe what is really happening, it is important to use a lot of different branches of sciences. So this is kind of very multi-scientific area where not only mechanics, by thermodynamics, statistical physics, kinetic theory, solid state physics, theories of stochastic processes, and mathematical physics, all these areas are essential. The background why this is very actual nowadays is because due to nanotechnology development, we are able to construct materials which really have each atom on its place. And in this case, ballistic heat processes appear to be much more prominent than it was thought about them before. Here you can see examples of ballistic heat transfer in 1D, 2D, and 3D solids. So how we describe these processes mathematically? As I said, diffusive heat transfer can be described by the heat transfer equation, which you can see here, and initial conditions. You have initial problem, which can be solved as it's shown here, like an integral. And what is important in this integral, you can see the Gauss function, which actually shows the shape of this solution. And this is the transfer function, which actually shows us that the heating zone is growing proportionally to square root of time. This is an essential feature of diffusive heat transfer. When we have ballistic heat transfer, the situation is different. This is example of heat transfer in the simplest model in the Hooke chain, which is shown at the top of the slide. And the solution can be also obtained in integral form. But here you can see the transfer function is proportional to time, and the shape function will have special form, which depends on the type of the crystal. And on the dispersion curve in this system. For example, for Hooke chain, you will have something like that. What is important, that if we look at this solution, and we can substitute the initial condition in the form of integral of delta function, we can see that what is happening here can be interpreted like a number of some quasi-particles which are represented by delta function, which are traveled through the system. This maybe is not very obvious from this representation, but if one considers from mathematical point of view, you can. It's really possible to see that this is just a number of quasi-particles traveling in the one-dimensional space. This kind of problems can be described by kinetic description. Which is described by Boltzmann equation, and its simplest form where the collisionless Boltzmann equation, where the density function, which is below, describes the density of distribution of particles in space and velocity. So velocity, space of coordinates and velocity. The kinetic description is a little bit unfamiliar for those who deal with continuum mechanics. Usually in continuum mechanics we have time and position, and here we have additional variable velocity. So we solve problem in the higher space dimension. But and when we solve it, then we can obtain the density as integral of the real density, mass density as integral of the density function. And also for kinetic description, we can write the initial problem. And then if we solve initial problem, then integrate it and then go to continuum description. What we will obtain? We obtain the representation you see here, absolutely similar to what we have for thermal transfer in solid. But what is obtained here? Here is just a description of particles which are moving in space. And here we have the description of heat transfer. So again, we have this similarity between particles and the heat. What is important that when we obtain this this equation, we actually solve the dynamics of lattice. This is very complicated process. We solve the equations of dynamics, then we use the continualization and so on, and then we obtain this equation. If we use kinetic approach, we obtain this equation just in several steps, as I showed here, just several lines, and you have this, you have the solution. So this is much easier. But the problem is, if one asks what is the quasi-particle, and you have some energy transfer, but you need to have this particle. What is particle? And also there are some other questions which are not very easy. You can see here the comparison between these two approaches. And now we will see the situation where kinetic approach really allows us to solve problem which is probably unsolvable in the case, no, up to now is unsolvable in the case we would like to find solution using just dynamics equations. The problem that at nanoscale heat transfer is ballistic, and at upper scales the heat transfer is diffusive. It is known from physics. But for many years it is a challenge how to show it on a simple lattice models. At the here you can see papers, and the first paper is by Professor Gendelman, who is probably listening us, and tomorrow will be his lecture, which is a great honor for us. In this paper, it was shown that in the chains capable for dissociation, so this is just simple chain, but if the distance between particles became bigger than some certain distance, the chain, the bond can break. And then it appears that in these chains couldn't be observed transfer from ballistic to diffusive behavior. This was shown numerically, and also there was some analytical arguments in favor of that. But this was analyzed on the steady state problem. And here we will try to analyze the same problem using unsteady approach and using kinetic analogy. What kind of analogy? We have this chain with breaks, and also we consider absolutely another system, moving particles, which we call gas, and gas with barriers. So why chain breaks? Because if you have a realistic interatomic potential, if particles go from each other, at one point they don't interact. So this is kind of break of the bond. We can model it by a simple way when we consider an elastic chain with just linear force, but if distance is bigger than some certain amount, it will break. This is the simplest way how we can model it. In gas, we do the same thing, but just we say that at some point randomly appears barrier, and then the particle which goes one way will go another way. If we think that in the solid travels some kind of quasi-particles which transfer energy, if there is a break, they will go to this break and then will be reflected and go backwards. So absolutely in the same way like you can see here with the particles in the gas. So what is advantage of the gas description? In this case, we can write kinetic equations, explicit equations, and we can solve them. So you can see here the the kinetic equation, and the right-hand side, which describes this reflection from random barriers. And then this equation can be what is happening? Can be transformed, and actually it can be transformed to kind of telegraph equation, which can be solved explicitly with the initial conditions which you can see here. Then what is very important, if we have a long time scale, then we can neglect the first term, and then we obtained a kind of diffusive equation, which should be valid for large times. And if we consider this diffusive equation, which is, this can be also solved analytically for density function, and then we integrate with have mass density, and we have the solution for diffusion in this system. Then we can do the following. So we have here the shape function, the initial conditions, and then what is important, we can decompose this solution in the following form, where we can have the transfer function and the shape function, and the transfer function will be equal to square root, so it proves that this is diffusion. And the shape function depends on the type of velocity distribution in the gas. If this is kind of photon gas, so you have only two possibilities of velocity c and minus c. In this case, you will have the classical shape function, which is known for diffusion, so the Gauss curve. But surprisingly, if we consider Hooke crystal, and then after integration, we have the shape function, which is different. It is represented in terms of k, where k is one of the Bessel functions, and it has a quite different form from the Gauss curve. I will show it a little bit later. Okay, so actually we solved problem for gas, and now this is a big question. If the result which is for valid for gas will be valid for the absolutely different system, the one-dimensional solid with brakes. So we will solve numerically these equations of this solid with the bond capable of dissociation. And then we calculate kinetic temperature as average over many realizations of this same random system. The randomness is in the initial conditions, initial velocities are random. And then after solution, we will have the following. This is solution for the crystal. Initially, you have some kind of heat distribution in the center, and after some time, you see the waves go around, and we have what we have. We will compare with the results of just a moment. So sorry, this was analytical solution which we were discussing for the gas. And here you have the numeric solution, which was done by integrating equations of motion, and comparing it, you can see that really the results are very, very similar, in spite of the fact that there is this absolutely different system. So it shows us that really the idea of that there are some kind of traveling quasi-particles in the crystal which reflect from the bond breaks really works. Also, if we go into details and look at what is happening with this shape function from the beginning to the end, we see that it changed from ballistic form to diffusive. But what is important that this diffusive form is really different from the Gauss curve. Gauss curve is shown in a black line here, but what is predicted by the theory, by the gas, is the red line, and what is shown by computation you can see in blue for the crystal. So you see that similarity is very well prominent. Here you also can see how changes the transfer function from the ballistic to diffusive way. For example, here you have change from square root to the linear behavior. If we look at what we have obtained, we see that ideal gas model really can describe what is happening in solid. But what is really unexpected, that obtained diffusive equation is a bit different. It is from one hand side, it's really diffusion, but diffusion of different, of a little bit different type. And what is also important, that if we go to these results obtained by Oleg Gendelman and co-authors, there was arguments, as I know, from Professor Antonio Politi, who is, I hope, also listening us, that these results of transfer from ballistic to diffusion will be not valid for sufficiently long time. So in this case, I argue that if we consider non-steady processes, but unsteady processes like here, we can speak about infinitely big time. For us, it is important what is happening at some certain time range. And we can see that at some certain time range, really, we can see this transfer from ballistics to diffusion. But the question, if this transfer is valid for any time scale, probably not, because for very big time scales, you will have you can again have something different. And our description, which we used, this kinetic description, also has its limitations. This is a question which should have additional need additional investigations. But what we know up to now, that in a simple Hooke chain without breaks, you can see that at different time scales, behavior is quite different. For example, this behavior, which we observe like ballistic heat transfer, at long times, this wave, ballistic wave, start to disassemble in some kind of which can be considered maybe as these quasi-particles, and that is show that at these big time scales, this description is not valid. And the same thing will be also probably for this diffusive description which we were considering. Also, at very big time scale, any description will be needed. So, very important thing for systems with microstructure, and in particular the systems with discrete structure, that it behaves differently at different time scales and at different space scales. And this scale range can be a lot of levels at which behavior can be different. And another question, what are really these quasi-particles used in kinetic description? Usually they are named phonons and the wave packages and maybe something else. But it is really interesting if we could observe them somehow in life, maybe in experiment or at least in computations. And one of the ways investigations we are doing just now is trying to construct and examine the behavior of this kind of particles in two-dimensional lattice. And this is a very interesting computation which was done by Professor Nikolai Bessonov, who is here. And we, with our co-authors, now try to examine this problem in more details, and probably in the nearest time we will speak about that and maybe next year. Okay, so probably this is everything I would like to say, and if you are interested in our publications, you can look at this internet site, and also there is a page devoted to page called Thermocrystal, devoted to thermal processes, and there you can see publications and some simulations and so on. So you are highly welcome. So thank you very much.
Well, thank you very much, Professor Krivtsov. And we have some time for questions. Please, Professor Nikolai Nikolaevich Smirnov.
Okay, thank you. Thank you very much, Anton Miroslavich. I enjoy very much always listening to your presentations or presentations of your co-authors on the topic of this ballistic heat transfer, because the topic is peculiar and interesting, and it has some characteristic features. And just I see the advantages on just placing everything in some order, but I will speak not about just the advances, but maybe about some drawbacks which I felt in this theory. And so just in my opinion, as being a mechanician, just not mathematician, so the beginning should be from some basic law or the process, because in the beginning of your lecture we saw different equations just describing diffusive heat transfer, ballistic heat transfer, different solutions. And so with this, just for example, equation for ballistic heat transfer, after we obtained some explanation that it can represent either just heat transfer in this just crystal, or just be analogy of some phonons or something in gas. So that is, but in my opinion, it would have been better just to begin with some, for example, generalization of the definition of temperature. What is temperature in general? Maybe it is not only chaotic motion, but just generalize it as kinetic energy of particles, which has chaotic component and just the component which is on the, and then from this point of, so this is the beginning, and then
can you show the presentation, please?
yeah, and then after this just the formulation of some law, energy conservation, or the conservation, yes, of energy with this, and then this equation with the second derivative should be somehow following from this law of conservation of something which you defined as being just generalized temperature, something, well, something like that. Maybe it's rather, yes. Yes, so, yes,
so
in a
this
crystal,
was the,
yeah.
yes, the definition for temperature.
This was the general, so the velocity, maybe I just missed it, but if this is the general definition, so this is the squared velocity of particles independent, which is not divided to just chaotic pulsations and transfer component.
You're absolutely right. Here, this is simplified formula, which is only for chaotic motion. In case if we have also some kind of long wave motion, we will add. So this will be not the average of square root, but of square, but it will be average of square minus this mean velocity.
This.
So actually here we have average over kinetic energy, but in the general case this should be kinetic energy related to the center mass of some, piece of material.
Yeah.
But here, if we consider just random motion, we can use only this formula, which is simpler.
Yes, definitely. So this is the just regular description for the temperature. But probably it's better just to introduce some also just the motion, the ballistic component in this description. Then it could probably provide just this equation, because now this equation.
Sorry, I missed. It's better to introduce. You mean this additional term?
Yes, additional.
Yes, this could be done, and this actually was done even in my book, which is published in 2007, when we describe this. Decomposition on two types of motion. This is essential in case of a nonlinear system. In this case, the linear motion will give you the mechanical processes, and then you separate somehow the. In this case, for temperature, you can just use the decomposition in terms, and you will have three terms. One will be zero, one will be mechanical, and one will be yes.
Yeah. And Anton Miroslavich, can you show the first or the second slide where two equations are present? Just
Which
for
slide?
For ballistic and in the beginning.
In the beginning. Okay, let's try. This one, probably, yes?
Yes.
Yes.
This one. So just the left slide, just the left-hand part, it shows just the energy equation within for some definite, with some definite limitation, some simplification. There is no motion of the just medium.
Yes, absolutely right. Yes.
And just the
also,
ballistic
diffusion equation also will be different if you consider the motion of media.
And this ballistic heat transfer, just it would be nice to see also which just basic law it represents, and within what type of limitations are used, just assumptions. So both equations should be derived from one energy law, but under different assumptions. So, well, that is, excuse me for being so eloquent, but that was the point which I wish to ask. I'm not expecting answer immediately, but
because we don't have time
for answer probably next year.
Yes. So maybe I will say the problem is that if we go into details here, so what somewhere here I think I showed this diagram, that really this can, unfortunately, this can't be done even in not in half an hour, not in 1 hour, and requires a course of lection to show all this. And here, of course, if I start from the beginning, I will not go to the yes. And now what I wanted to show, and that we really can describe what is happening in solid using analogy with gas, and it really works very well. And equations which are used for gas is just, you understand, each ideal gas, each particle is moving, the impulse momentum is concerned, that's it. For chain we use, we use the Hooke law, and also we allow it to. So this is what is essential. Everything is based on the simple mechanical laws, nothing else, nothing, no mystery, just conservation of momentum, and that's it, and all what is done. But the problem is that for discrete systems, due to these different scale levels, we can obtain from this simple ideas, very complex behavior.
Thank you very much, Nikolai Nikolaevich.
From online, there is no.
Yes, I wanted to say that there must be some questions from online audience, as I remember. Can you please switch?
I don't know if we have time.
We have. So please, Professor Tar.
Yeah, hi. I mean, I had this about the form of the this heat peak. So you showed that it's diffusive but non-Gaussian. I mean, do you have some understanding of like I was thinking like in terms of a quasi-particle picture, is there a kind of some sort of modified random walk which would give such a like it's diffusive but non-Gaussian? I mean, is there some understanding of this?
Oh, this is very interesting question, and up to now, to tell the truth, I don't know the exact answer. It's really not Gaussian. It's we have the explicit equation for that. This is one of the Bessel functions, and why is it so? We have several ideas why it can be. Maybe because the in reality, this break in the real system, if we have realistic potential like Lennard-Jones, for example, this break will not be instant. It will take some time, and this will give give something like smoothness. But this should be investigated additionally. Probably one of the ways to investigate what is happening in the same Lennard-Jones system, and will it be this kind of curve with point or not? Mystery.
Yeah, thanks.
Thank you, Professor. So please, we have some time for questions. Professor Yermeyev.
Okay. First of all, I thank you for the nice presentation. I have maybe naive question. You concentrated on nanoscale problems, but maybe this idea could be transmitted into another problems when you have some kind of strongly inhomogeneous materials with particles, interacting particles like mixtures, soils, and so on. What do you think about this?
Yes, Victor, thank you. Thank you very much. Actually, what we are considering, and this idea of these quasi-particles which transfer energy, this can be, I think, very straightforward transfer to idea of what is happening in solid, continuous solid with kind of internal structure. Actually, probably the same thing, not probably, up to now we are really investigated this kind of systems, and like in discrete system, also in continuous system, these waves, kind of quasi-particles can be found, and the same laws could be fulfilled. So this really could be done. The only thing is that the discrete system from some points are easier to analyze, but of course from some other point of view they are more complicated. So this is really a very promising way of direction of investigation, up to my mind.
Okay, thank you so much.
So let us thank the speaker again.